Section 4.5, Solving Quadratic Equations by Finding Square Roots. So we've solved quadratic equations by factoring, and this is just another method. And so in order to be able to solve quadratic equations by finding square roots, there's two kinds of numbers. There's perfect square numbers and their corresponding square root numbers. And you should become familiar with at least the first 15 of each of these pairings of numbers. It's going to make doing this section and your future math much easier. And so the square root numbers, well, any integer can be a square root number. Basically, they're called perfect square numbers because if I were to have a square and both sides were, for example, 3 by 3 square, then that's why you get that the perfect squares are going to be when you multiply a number by itself, because you will get a perfect square. So 1, 4, 9, 16, 25, and so on. And you should become familiar with, if you're not already, at least these first 15 perfect square pairings. And so then in using these perfect square numbers and their square roots, we need to become familiar with two very important properties of square roots. And the first one of those is that if I'm multiplying two numbers together underneath the radical, I could break this up into the square root of a times the square root of b. And so you can break a number up into any pair of its, or any three if you'd like, of its factors. And then the other property is that by division, if I have the square root of a over b, I could rewrite this as the square root of a over the square root of b. And then this enables us to simplify square roots a little bit more. Simplifying square roots, what this means is that there are no more perfect square factors underneath the radical. And so that's why we're going to use those previous properties to break numbers up to get those perfect square factors out from underneath the radical. And so the first example, the square root of 75. Well, 75 isn't a perfect square number, but 25 is. And so we could rewrite 75 as the square root of 25 times 3. Then using that property of square roots, this is the square root of 25 times the square root of 3. And then the square root of 25 is 5, and we can't simplify the square root of 3. So our answer would be 5 times the square root of 3. Our second example, the square root of 11 over 144, well, I can break this up into the numerator and denominator. And of course the square root of 11 can't be simplified. There's no perfect square that divides evenly into it. It's a prime number. But the square root of 144 is 12. So my answer would be the square root of 11 over 12. Continuing on with a couple more examples, the square root of 7 times the square root of 35. Well, neither of those have a perfect square factor in them, but I could multiply them together and get the square root of 245. And now if I look at my list of perfect squares, if I start with the 121, doesn't divide evenly into 245, nor does 100, nor 81, nor 64. And you can find these, obviously, if you can't do this in your head, by putting it in your calculator. But you'll see that 49 divides evenly into 245, and it's 49 times 5, which I think can then break up. And then the square root of 49 is 7, and I'm left with also the square root of 5. Next example, the square root of 100 over 169. Well, the square root of 100 is 10, and the square root of 169 is 13. So I didn't actually write this as two separate square roots, but hopefully you get the idea that we could, and we just skipped one of those steps. And now this problem we could actually do in two different ways. So the first thing I'm going to do, I'm going to show you, this is what you saw first, you could write it as a square root of 27 over the square root of 36. 27 can be broken up as to 9 times 3, because 9 is a perfect square. And the square root of 36 is 6. When I simplify that numerator, the square root of 9 is 3, but I'm still left with this square root of 3 inside the radical. And of course it's over 6. And then I can simplify 3/6 into 1/2. So you could write that 1 there if you want, but you don't have to. And so the square root of 3 over 2 would be my final simplified answer. The other way you could do it, if you recognize that 27/36 was 3/4, and then if I did write it as the numerator and denominator, well, now I'm it's already simplified, so I have the square root of 3, and then the square root of 4 is 2, and so I end up with the same final answer. Now another thing that we need to do is to be able to rationalize the denominator, and what rationalizing the denominator means is getting rid of the radical in the denominator. So there's three ways that this might occur. First of all, if you just had a square root of a number in the denominator, well, if I multiply it by itself, top and bottom, so I'm multiplying by 1, then you would get the square root of b squared, and of course the square root and the squaring undo each other, and so I would be left with b. I could also have a plus the square, or a number plus a radical, in which case I would multiply by what's called its conjugate, and that would be a minus the radical, so the exact same numbers. Or if I started with a minus the radical, then I would be multiplying by a plus the radical. And so let's go ahead and see what happens if we multiply these two factors together, or these two factors, depending on how you write them, what order you write them. So a times a is a squared, and then I get minus a times the radical b, and then plus a times the square root of b, and then minus the square root of b squared, because remember we're multiplying what's inside the radical by itself. And so then of course my two middle terms are positive and negative of the same value, so they cancel, and I have a squared minus, and again the square root and the squaring undo each other, so I have a squared minus b. And you'll notice that both of these simplified answers, there's no radical. So if either of these, any of these cases are in the denominator, then that's what you'd have to do to get rid of it. So let's look at a couple examples. If I have the square root of 9 over 8, well, I could break this up, of course. And then the square root of 9 is 3. The denominator is 4 times 2, the square root of that. And so I have 3, and then the square root of 4 is 2, and I still have this square root, that 2 inside the square root. But now I can't have a radical on the denominator. So I need to multiply, and of course I'm multiplying top and bottom because I'm actually just here multiplying by 1, so I'm not changing the value of my fraction. On the numerator I have 3 times the square root of 2, and then on the denominator I have that 2 times the square root of 2 times the square root of 2 is the square root of 4, which is in fact 2. Simplifying my denominator, I get 3 times the square root of 2 over 4. Let's look at another one, the square root of 8 over 3. Again, if I break this up, the numerator and denominator, I can't have a radical on the denominator, so I'm going to multiply top and bottom by the square root of 3. On the numerator, when I multiply the square root of 8 times the square root of 3, I can multiply those two numbers together and get the square root of 24. And then in the denominator, the same thing, I would get the square root of 9, which of course is 3. But now, keep in mind that I can simplify this a little more, because 24 is 6 times 4. Since 4 is a perfect square, I need to pull out that perfect square factor. And it's still over 3. So the square root of 4 is 2. And I still have the 6 inside the square root, and then of course it's over 3. And so that would be my simplified answer. I can't simplify the 2 and the 3, and there's no perfect squares left in the square root of 6. And now let's look at one that we have to multiply by the conjugate. So you'll see on the denominator I have 5 minus the square root of 2, so I need to multiply by the conjugate of that, which is 5 plus the square root of 2. But of course I need to multiply by 1 so I don't change the value of the fraction. So I need to multiply the numerator times the same thing. When I distribute the 4 in, I get 20 plus 4 times the square root of 2. And when I FOIL out, multiply out the bottom, I get 25 plus 5 times the square root of 2 minus 5 times the square root of 2 minus the square root of 4. So of course my two middle terms on the denominator are going to cancel. And square root of 4 is 2. When I simplify my denominator, I get 20 plus 4 times the square root of 2 all over 23. But I want to write this as two separate terms, so that would be my final answer. Alright, so now we're going to solve some equations using square roots. And how do you know that you're going to try to do this as opposed to trying to factor? Well, I'd like everybody to come in with some sort of idea about why you're going to do this. That's how I'm going to start class. I'm not going to tell you the answer, but I want to see if you can figure out how you can determine that you can just use square roots to solve. And so the first thing we need to do is get our x by itself. And since I only have one x, first thing I need to do is, of course, add the 15. 2x squared equals 80. Dividing by the 2, I get x squared equals 40. And of course, how do you get rid of the square? You undo squaring by taking the square root of both sides. So x equals plus or minus the square root of 40. Now, previously in this section, when we've been taking square roots, since we were dealing with just problems in exercises of square roots and simplifying them, we didn't worry about the plus or minus. But if you think about it, the square root of 4 can be 2 because 2 times 2 is 4. Or it could be negative 2 because negative 2 times negative 2 is 4. So when we're solving equations, you need to realize that the answer could be a plus or minus. And now, of course, we can simplify the square root of 40. The largest perfect square that divides evenly into it is 4, so I can rewrite it as 4 times 10. And then, of course, the square root of 4 is 2, so my answer is x equals 2 square root of 10 or negative 2 square root of 10. So yes, you can use the plus or minus. So now let's look at another one. Again, we need to get our x squared term, or our x, by itself. So adding 8, I get that x squared over 3 equals 6. Then, of course, we're dividing by 6, so I'm going to undo that by multiplying. Sorry, we're dividing by 3, so I'm going to undo that by multiplying both sides by 3. So I get x squared equals 18. Undo the squaring by taking the square root. So I get x equals plus or minus the square root of 18. And again, of course, I can simplify that. The largest perfect square that divides evenly into 18 is 9. So my final answer would be x equals plus or minus 3 times the square root of 2. And the last one of these kinds of problems is equal to 27. So I need to get what's being squared alone before I need to undo everything to get back to the x. So the first thing I need to do is get rid of that 1/3. I can't distribute that 1/3 in because of the power on the parentheses. So then I get x minus 4 quantity squared equals 81. So again, the next thing I need to do to work back to the x is to take the square root of both sides. So now I have x minus 4 equals plus or minus 9. Now you need to be careful here because we're not going to get an answer of plus or minus the same thing. You need to write this as two separate equations to solve. X minus 4 equals 9, and x minus 4 equals negative 9. That's the whole point of that plus and minus. Solving the first one, I get x equals 13, or x equals negative 5. So two distinct answers, so be careful. And finally, of course, we have word problems. Dropped objects, and this formula is also in your book. When an object's dropped, its height above the ground after t seconds can be modeled by this equation. H is always going to be the final height. Where is the object ending up? T is going to be your time, and it's going to be in seconds. And h sub 0 is how that's read, is the initial or the starting height of an object. And just so you know that the negative 16 is Earth's gravity coefficient, so that's going to be a constant that's always going to be there. It's going to be a different number if we happen to be dealing with meters per second. So, let's change this problem a little bit. The stratosphere in Las Vegas is 1,149 feet tall. When you're at the top of the ride, you look down over the edge of the seat and your sunglasses fall off your head. How long will it take until your sunglasses shatter on the ground below you? So we're going to use this formula, and the final height, if it's landing on the ground, my height will be 0. I'm trying to find how long, so of course I need to solve for the t, and the starting height of my glasses is 1,149 feet. Solving this, I need to get the t by itself, so I'm going to add the 16t squared. Dividing by the 16, I get that t squared equals 71.8125. Taking the square root of both sides, I get that t is 8.474. Now, of course, it would normally be plus or minus, but we're obviously not dealing with a negative time. So make sure you're also careful about the plus and minus in a real-world situation. So it's going to take about 8.5 seconds for your glasses to reach the ground. Wow, that's high. Let's see for a second, how long would it take to land on the top of a double-decker bus that's 15 feet off the ground? Well, the only difference in this problem is that instead of landing on the ground, my final height is going to be 15 feet. The rest of the problem is going to be the same. So if we go ahead and solve this, we wouldn't expect, if it's only a 15-foot difference of 1,149 feet, that the time would be that drastically different. And it's not, so it's still going to be close to 8.5 seconds, a little bit less, obviously. Alright, and that does it for solving equations by using square roots. Remember to go back and do the notes check. And if I went through some of the examples too fast, please make sure you come to class with some questions about them. We'll see you tomorrow.